Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on group, lecture number 64, in which I will discuss some theorems and problems on complexes of a group. Now we prove a theorem. Theorem is if H and K are two subgroups of a group G, then HK is a subgroup of G if and only if HK equal to KH. Now we prove this. Given that H and K are subgroups of group G. Therefore, H inverse equal to H, K inverse equal to K, H inverse equal to H, and K inverse equal to K. This is number 1. Now let HK equal to KH. This is number 2. We have to show that HK is a subgroup of group G. Now HK multiply HK inverse equal to HK inverse means K inverse H inverse equal to H K inverse H inverse. Since associative law holds for the multiplication of complexes, this equal to H, here K inverse, K inverse equal to K, and H inverse. This is using 1. Equal to KH. HK equal to KH using 2. Using 2. And by associative law, K H inverse. Associative law. And this equal to K H inverse equal to H in using 1. And KH equal to HK using 2. Therefore, HK inverse equal to HK. Since if H inverse equal to H, then H is a subgroup. So here HK inverse equal to HK implies that HK is a subgroup of group G. Conversely, let HK is a subgroup of group G. We have to show that HK equal to KH. Since HK is a subgroup of G, implies that HK whole inverse equal to HK, implies that K inverse H inverse equal to HK, K inverse equal to K, since K is a subgroup, and H inverse equal to H, since H is a subgroup, this equal to HK. So KH equal to HK or HK equal to KH. Proved. Now we prove a theorem so that if H is a subgroup of G and N is a normal subgroup of G, then H intersect N is a normal subgroup of H. Given that H is a subgroup of group G and N is a normal subgroup of group G. Therefore, H intersect N. H is a subgroup of G and N is normal subgroup of G. That is, N is a subgroup of G. We know that intersection of two subgroups is a subgroup. Therefore, H intersect N is a subgroup of G. Here, this is group G. Here, N normal subgroup of G, and this is H, a subgroup of G. And this part is intersect of H and N. This part. Since H intersect N is subset of H, implies that H intersect N is a subgroup of H. Now, let small h1 belongs to H and A belongs to H intersect N implies that H1 belongs to H, A belongs to H and A belongs to N. This is number 1. This is number 2. Since capital H is a subgroup of group G, therefore small h1 belongs to capital H implies that small h1 inverse belongs to capital H. This is number 3. From 2 and 3 we get H1 belongs to H, A belongs to H, H1 inverse belongs to H implies that H1 A H1 inverse belongs to H by closure property. This is number 4. Again, H1 belongs to H implies that H1 belongs to group G because H is a subgroup of group G and H1 inverse belongs to group G. This is number 5. From 2 and 5 we get H1 belongs to group G, A belongs to N, and since N is a normal subgroup of G, implies that H1 A H1 inverse belongs to N. This is number 6. From 4 and 6 we get H1 A H1 inverse belongs to H intersect N because H1 A H1 inverse belongs to H and H1 A H1 inverse belongs to N, common element of H and N. This is number 7. Since H1 belongs to capital H and H intersect N is a subgroup of capital H, therefore from 7 H intersect N is a normal subgroup of capital H. Proved. Now we prove a theorem. Theorem is a normal subgroup is commutative with every complex. Now we prove this. Let N be a normal subgroup of A group G and H be a complex of group G, let H1N1 belongs to Hn, H1 belongs to H, N1 belongs to N. This is number 1. Now H1N1 equal to H1N1 identity element. This is equal to H1N1 H1 inverse H1, identity element equal to H1 inverse H1. This equal to H1N1 H1 inverse H1. Let this is number 2. Since H1 belongs to H and H is subset of G, implies that H1 belongs to G. Since N is a normal subgroup of G, therefore H1 belongs to G, N1 belongs to N, implies that H1 N1 H1 inverse belongs to N, implies that, let this is equal to N2, N2 be the element of N, belongs to N, let H1 N1 H1 inverse equal to N2. This is number 3. Therefore, from 2 and 3, we get H1 N1 equal to N2 H1. N2 H1, N2 belongs to N and H1 belongs to H. This belongs to NH. This is number 4. From 1 and 4, we get H1N1 belongs to Hn, implies that H1N1 belongs to NH, implies that Hn is subset of NH. This is number 5. Now let N3 H3 belongs to NH, N3 belongs to N, H3 belongs to H. This is number 6. N3 H3 equal to identity element E N3 H3. This equal to H3 inverse N3 H3. This equal to H3 inverse N3 H3. This is number 7. Since H3 belongs to capital H and capital H is subset of G, implies that H3 belongs to G. Since N is a normal subgroup of G, therefore H3 belongs to G, N3 belongs to N, implies that H3 inverse N3 H3 belongs to N, implies that H3 inverse N3 H3 equal to, let N4 belongs to N. Let H3 N3 H3 inverse N3 H3 equal to N4. This is number 8. From 7 and 8 we get N3 H3 equal to H3 inverse N3 H3 equal to N4. This belongs to H N. Since H3 belongs to H, N4 belongs to N. This is number 9. From 6 and 9 we get N3 H3 belongs to NH, implies that N3 H3 belongs to HN, implies that NH is subset of HN. This is number 10. From 5 and 10 we get HN equal to NH. Therefore, commutative. Proved. Now we solve a problem. Problem is N is a normal subgroup and H is a subgroup of a group G. Then NH is a subgroup of G. Now we prove this. Given that N is a normal subgroup of group G and H is a subgroup of group G, implies that H is a complex of group G. Therefore, NH is commutative, that is NH equal to HN. Since N is a normal subgroup, implies that N is a subgroup and H is also a subgroup of group G. We know that NH is a subgroup of group G if and only if NH equal to HN. This is number 2. From 1, we get the same result. Therefore, NH is a subgroup of group G. Proved. Now we prove the next theorem. Theorem is, if H is a subgroup of G and N be a normal subgroup of G, then N is a normal subgroup of Hn. Now we prove this. Prove. Given that H is a subgroup of group G and N is a normal subgroup of group G, implies that Hn is a subgroup of group G. Let N belongs to normal subgroup N, number 1. Let E be the identity element of group G, implies that E be the identity element of subgroup H. Therefore, E belongs to H, and since N belongs to normal subgroup N, implies that En belongs to Hn, implies that En means N belongs to Hn. This is number 2. From 1 and 2, we get N belongs to N, normal subgroup N, implies that N belongs to Hn, implies that N is subset of Hn. This is number 3. Since N is normal subgroup of G and Hn is a subgroup of G, such that N is subset of Hn, implies that N is a subgroup of Hn. This is number 4. Now let small n belongs to normal subgroup N and H1N1 belongs to Hn. H1 belongs to H, N1 belongs to N, normal subgroup N. Therefore, H1N1 N H1N1 whole inverse equal to H1N1 N1 inverse H1 inverse. This equal to H1N1 N1 inverse H1 inverse by associative law. This is number 5. Since N1 N1 inverse all belong to N and N is a normal subgroup of G, then by closure property N1 N1 inverse belongs to normal subgroup N, implies that let this equal to N2 belongs to N, N1 N1 inverse equal to N2. This is let. This is number 6. From 5 and 6 we get here H1 N1 in H1 N1 inverse equal to H1 N2 H1 inverse, and this belongs to N. Since H1 belongs to H, implies that H1 belongs to group G and N is a normal subgroup of group G. This is number 7. Therefore, H1N1 belongs to Hn, N belongs to N, capital N, normal subgroup N. Then from 7 we get H1N1 in H1N1 inverse belongs to N, implies that N is a normal subgroup of Hn. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.